Okay, so in this problem, what we have is a wheel, which is like right here, and there's like a blue rope attached to it, and then there's a stone attached to the rope, which is like right here. That's the stone. And so the stone has a mass, and what's going to happen is it's at rest initially, and then we're gonna drop it, and it's gonna fall 12.6 meters. So it's right here, and it's gonna fall down, and it's gonna fall 12.6 meters in 3 seconds. And the wheel at the top has a mass of 10 kilograms and has a radius of 0.3 meters. The question is, what's the tension in the rope? So there's a rope here, right, between the wheel and the stone. What is the tension in the rope? And also, what's the mass of the stone? Okay, so we're going to figure out what both those are. Remember, we're looking for the tension in the rope and the mass of the stone. Okay, so it says it fell 12.6 meters in 3 seconds, right? So we can just do normal linear kinematics on that. So what I can do is I can say, all right, I can create like a graph here. I can do velocity versus time. The initial velocity was 0 because it was at rest. The stone, we're talking about the stone here. And it's going to fall down. Now, so the velocity versus time, the graph is that we're going to make is acceleration, right? But is it constant? Like, what is it? So it's going to be constant. You're like, well, how do you know it's constant? Because this thing is pulling down with a certain force, and that force doesn't change. Like whatever it is. Well, gravity, of course, is pulling down, which is a force. And then the wheel, right, this wheel is going to resist it because it has inertia. So it's going to try to resist that. But none of these things are changing, right? Like the amount of inertia and the resistance is not going to change. Gravity's not going to change. So whatever it is going to be constant throughout the whole thing. So the acceleration down here, or this graph, is going to be constant. So it's going to be a straight line. And so the velocity versus time graph, the actual function represents acceleration, or the slope, if you will, represents acceleration. Okay, so what we have here is, and I can pick some time here. Let me just erase this other one. Actually, I know what that is. So initially, so on the bottom is 0 seconds, and then it says it fell for how long? 3 seconds. So I know this is 3 seconds. And it says it fell 12.6 meters. So remember the velocity versus time graph. The area under the curve represents displacement. In this case here, it's 12.6. That was already given to us, right? So what we can do here is we can just do, some normal algebra. We can say the area, of course, of a triangle is 1/2 times the base times the height. You're like, where's the triangle at? The triangle is here, right? There's a triangle right there. Okay, so the area is 12.6. Half. The base is 3. And so the height is what we're looking for. All right, so all we have to do is just solve for h. If you do that, you get 8.4. So h is 8.4. That's the height. So that represents the velocity, right? So here we are. This is 8.4. And this is, of course, is in meters per second because that's the velocity. All right, great. So now I know the velocity at the end of 3 seconds. So can I figure out the acceleration then? Because I kind of want, what I would like to know is how fast is this stone accelerating down? Well, you may remember that acceleration is, it's dv dt. That's for instantaneous acceleration. But as you can see here, the acceleration is not changing over this time. So you don't really need dv dt. You could just do delta v delta t, because it's not changing. So we can just pick any time frame. So you can go from 0 to 3 if you want to. So the change in velocity, of course, is 8.4. it went from 0 to 8.4, and the time went from 0 to 3, so it's 3. So if you do that, you end up with 2.8. 2.8. So that's the slope, and that slope represents the acceleration. So, and you could, if you wanted to, say the velocity as a function of time is 2.8 t plus 0. 0 meaning the y-intercept, or the initial or starting conditions. Okay, and so if you took this and so that's the velocity, right? Okay, so that looks cool. And remember, if you wanted to find the acceleration, remember, so acceleration is the derivative of the velocity with respect to time, and that's, was it 2.8 t plus 0 with respect to time? And so if you take the derivative of that, what do you get? 2.8. Okay, and that's in meters per second squared. So if you take the derivative, obviously, of the velocity, you're going to find acceleration. And so that's what we have here. We have 2.8 meters per second squared. So let me just highlight the velocity, 8.4 meters per second, and the acceleration right here, which is 2.8 meters per second squared. Great. So now I know the acceleration. So normally, if something were dropped on the Earth, it would fall at 9.8 meters per second squared. But this is going 2.8. Why is it going slower? Well, the reason it's going slower is because this wheel is resisting that acceleration. It's resisting it, right? That's what mass does. If it's linear mass, it's going to resist changes in its like speed and in its direction. But if it's moving in a circle, then that circle is going to resist, changes in torque. So basically, if you're moving linearly, it's a change. If the force changes, if the acceleration changes, it's going to resist that. Well, in both cases, it's going to resist acceleration changes. But in the circle sense, it's more like torque. It's going to resist torque changes in torque. Versus linearly, it's more like it's going to resist changes in. So basically, if you have a net force on an object, linearly, then it'll resist that. But if it's a circle, if it's moving a circle, it'll resist net torque, a net torque change. Okay. All right. So now we have acceleration. Now I have acceleration. What I'd like to do is maybe turn that into, that's linear acceleration. I'd like to turn that into angular acceleration. And of course, you may remember that acceleration. Whoops, let's go back. Nope. Acceleration is just angular acceleration. Linear acceleration is just angular acceleration times the radius. So, but of course, you can do the opposite of that. You can just do divide by r, and then you could have alpha equals a divided by r. A, we already have that, 2.8. R is 0.3, and that'll give me my alpha, which is 9.3. 9 equals 9.3, and that's in radians per second squared. Okay, so now I know how fast this thing is spinning in radians per second squared. I know it's acceleration. All right. Okay, so that's cool. So now that I know that, maybe I could figure out the torque on this wheel. And so you may remember the torque is equal to IA, or I alpha. And so torque is what I'm looking for. I is the moment of inertia. Now this is a solid disk. And so the inertia of a solid disk is 1/2 m r squared. Half mass is given to us, it's 10. R is 0.3 squared. If you do the math on this, I'm not sure what it is off the top of my head, but anyway, but you can do that, and you'll know. We'll just call it I. Well, so whatever that is. And then you have I, which is just given to us from here. And then you can multiply that, times alpha, which was given up here, times 9.3 radians per second squared. Okay, so basically it's 1/2 times 10 times 0.3 squared times 9.3. If you do all that, you'll get the torque, which is 4.18. So this is torque is equal to 4.18 Newton meters. Okay, so that's the torque on it. On the wheel, right? That's the torque on the wheel. So remember, if something is moving linearly, then you have, if it's accelerating, I should say that if it's accelerating, you have a net force on it. If it's accelerating circular in a circular path, it has a net torque, right? So are we talking about a net force or a net torque? And here we're talking about a net torque, okay? Because it is accelerating. The reason it's accelerating is because there's a stone on it. The stone is accelerating linearly, so therefore the wheel is accelerating circularly. Okay, so what I need to do is I need to find out the tension on this line, right? The tension on this line. And so, okay, so let's just go back to this. So I'm trying to look for this tension, right? And tension is a force. And so is there somehow where I could figure out, I know the torque, I know this wheel, and I know it has a torque. But there's somehow how I could convert that torque into a force. And yeah, you may remember that torque is also equal to force times distance. Well, that's the simplified version. As long as the force, and let's say this is the pivot point here, and let's say my force is like this. As long as the force and the lever arm are at 90 degrees, then you can just multiply them together. If they're not, you're gonna have to straighten them out. You're either gonna have to find the component of the force that is perpendicular to the lever arm, or you're gonna have to move the lever arm until it's perpendicular to the force. Either way, you're gonna have to move one or the other until they're at 90 degrees. Once you do that, then all you have to do is multiply them together. Now, look, check this out. So I have this thing. So this thing pivots here, right, in the center. That's where it pivots. So the lever arm, you could think of it as this. This is the lever arm, okay? And how long is that? 0.3. Now, where's the force at? Well, because this thing is pulling straight down like this, the force is also going straight down, right? So there's your force. Your force is pulling straight down. And the lever arm, so the force is like completely vertical, and the lever arm is completely horizontal. And of course, those are at 90 degrees to each other. So, torque, remember, is force times distance. But I'm looking for force, remember, because I'm looking for the tension in the line. So all I have to do is divide by distance. All I have to do is divide by distance. And force is equal to torque over distance. Torque is given. Not given, but we just calculated it, right? 4.18 Newton meters. And then the distance is, that's the radius, right? 0.3. And if you do that, you'll get about 14 newtons. Okay, so that's the force, which also equals the tension in the line. So this tension here, maybe we can make that yellow. So the tension is 14 newtons, roughly 14 newtons. Let's erase that. It looks terrible. Let's try that again. Remember, if you're like, well, how do you know it's 14 newtons? Because you're trying to find the force on that wheel, because the wheel is attached, right? The wheel is attached to the line. And so what is the force on that wheel? So all you have to do is just find its torque, divide by distance, and now you know what the force is, okay? And so that force is the same force on the rope, which is tension, okay? So I have 14 newtons. Let me also make that yellow, because why not? Okay, now the last piece of the puzzle. The last piece of the puzzle is, what's the mass of the stone? Okay, so you may remember from Newton's second law, the sum of the forces, in this case here, y, because we're only moving in y, is equal to the mass times the acceleration also in y. Now, if you're trying to get tricky, you may think to yourself, oh, well, I have a torque which is the force, and it's going up from the perspective of the stone. So let's say this is the stone, right? From the stone's perspective, right, the tension is pulling up, and then mg, or the weight, is pulling down. So remember, from the perspective of the stone. So then you may go, oh, well, okay, so the tension is going up, minus mg is going down, and then I'll do mass times acceleration in y. Don't do that. I did this before, and you'll end up getting it wrong, because you're trying to outsmart the equation, I suppose. Because you're like, oh, well, torque is up, and then mg is down, so it's a negative. No. The problem is that g is already negative, because g is acceleration due to gravity, right? And that acceleration vector is already negative. So g is already negative. So if you're doing a negative of a negative, you're making it positive. So basically what you should do is just do what this equation says and just sum them up. Say t plus mg, because the negative is inside the g already. And then you say ma. We'll just do ma. Y is assumed. Okay, and so now what I'm trying to look for is mass. So what I can do is I can move the mg over, so I can say T equals ma minus mg. Then I can pull the m out, a minus g. Right? And then I can say equals T, and then basically it's T over a minus g. Equals m. We'll get rid of that. We'll get rid of that right there. Okay, that looks pretty good. Now, so what is a minus g? So a is actually negative, right? So you have to think about, what is a? A is the acceleration of the stone going down. Remember, it was, let me look for it, 2.8. So a is 2.8. But is that going up or down? It's going down, right? So a is actually negative. So it's actually a negative 2.8. Minus, and then g is negative. That's gravity, right? Gravity is not negative 9.8. So that if you look at that, what's going to happen here is the negatives cancel. So you end up with basically a plus. So you end up with plus 9.8 and then a negative 2. And then the tension, we already had the tension, and the tension was about 14, right? Roughly 14 newtons. Okay, and that's positive, right? Because it's going up from the stone's perspective. It's going up. So you effectively have 14 on the top, and then plus 9.8 and then minus 2, and you end up with roughly 7, positive 7. And so 14 over 7 is 2 kilograms. So that is the mass of the stone. So the tension on the stone above it is 14 newtons, which is that's what's preventing the stone from really accelerating at 9.8 is the tension. Remember, the tension, what's the tension from? It's because the wheel has inertia and it doesn't want to spin. It doesn't want to accelerate, right? It doesn't want to accelerate. You're trying to change its torque. It says, oh, I have a net torque on me. It doesn't want to change it. So that tension is because the wheel doesn't want to accelerate. It doesn't want to accelerate. Yeah. So the tension is 14 newtons, and then the mass of the stone is 2 kilograms. And just to remind you again, when you're doing these, the Newton's second law, don't try to outsmart it by going, oh, mg is actually negative. No, don't do that, because the g is already negative. And so, yeah, basically I ran into this problem before where I was like, oh, yeah, it's negative. No, it's not. The g itself is negative, so you don't put in another negative, right? So the formula is the sum of the forces in y. Sum meaning add. So you have to just add all the forces. And then if the variables happen to be negative, then it'll be negative. If they're positive, then it'll be positive. Okay. All right, that should be about it.